All right, Jennifer, Olivia Morales. Okay. Oh, okay. 3, 4, 5, 6, 7, 8. Okay, ladies and gentlemen. Today we're going to finish up periodic trends. We're going to talk about VSEPR theory. Last day for retakes and missing work is tomorrow, ladies and gentlemen. Again, there are some of you who the difference between you passing and failing this class will be if you turn in any labs that you are missing. Because if you don't, you're probably not going to pass. Because here's the thing, ladies and gentlemen, I've looked at your grades. Some of you have not yet passed the test, so I don't know how you're really going to pass the Unit 8 test. But again, it could be possible, okay? And someone could walk on water and part a Red Sea. But again, there are possibilities out there that exist, ladies and gentlemen. So keep that in mind. Okay, here we go. Here's your first question today. Which of the following is not a property of a metal? Move your cursor to the one that is not a property of a metal, ladies and gentlemen. Good, ladies and gentlemen. The correct answer is being brittle. Being brittle is not a property of a metal, ladies and gentlemen. Being brittle is actually the opposite, is a property of a non-metal, and it means things can break easily. Which of these metals is the more reactive metal? Of these four, which one is the most reactive metal, ladies and gentlemen? Wait. Okay, I waited. Now what? For what? Cesium? It's this one right down here.
Oh, okay.
55. It's an element on your periodic table.
Thanks.
Number 55 on the table, but number 1 in your heart.
Okay.
Cesium is the correct answer, ladies and gentlemen. It is the one that is furthest down and the furthest to the left. It is the one that is closest to francium, therefore it is the most reactive metal. Which is the most reactive non-metal, ladies and gentlemen? Of those four, which is the most reactive non-metal? Tellurium. Tellurium is Te. It is right here. It is number 52 on your periodic table, but number 2 in your heart because cesium is number 1.
No,
Cynthia is not an element on the periodic table because then it would be a lot less annoying. I mean,
okay.
So you're saying
who said I was talking about you, Cynthia? There's other Cynthias in the world.
You're not in this room.
You're
That's
saying
so
that the
crap that I
periodic
said
table
in
would
like
be better
kindergarten.
with You're so right.
I'm sorry, what was that?
You just said that the periodic table would be better with Cynthia on it.
Okay.
That's what you just said, isn't it? You
Okay.
said it'd be a lot less annoying.
Exactly.
Okay.
Okay.
So if you're going to interpret that as being better, maybe some people like it to be annoying.
Are you
Okay,
just mad at
final
me?
answer, ladies and gentlemen. Oxygen. Oxygen is the one that is closest to fluorine, which is the most reactive non-metal. Which element has the largest atomic radius, ladies and gentlemen? Of these four elements, which one has the largest atomic radius? Now, let me help you out because you seem to be a little bit confused. Here is calcium, ladies and gentlemen. Here is gallium, ladies and gentlemen. Here is bromine, ladies and gentlemen. And here is argon. So which of these four would have the largest ionic radius, ladies and gentlemen? The correct answer? Calcium. That correct answer, ladies and gentlemen, is wrong.
What?
Should be bromine. Bromine.
Why?
Why? Because there's the one-time jump. Calcium and bromine are in the same period. So ionic radius decreases as you go across, but when you get to this line, there is a one-time jump. And these nonmetals are all bigger than these metals. So the correct answer should be bromine, ladies and gentlemen. Sorry about that. I will correct it later on. Bromine. Questions? Wonderful. Which of the following elements has the largest ionization energy? The largest ionization energy, ladies and gentlemen. Here's sodium. Here's aluminium. Here is chlorine. And here is argon. Correct answer, ladies and gentlemen, is argon. Noble gases always have the highest ionization energy. Why?
It's always the right.
But why? Why do the ones all the way to the right, why do the noble gases have the highest ionization energy? Yes. An ionization energy is the energy needed to remove an electron from something. And the noble gases are stable and they do not want to give up an electron. They're stable. They don't want to give up an electron. They're like, ain't happening. You can make them give up an electron, but you have to use a lot of energy compared to any other element. Questions, ladies and gentlemen? No? Wonderful. Excellent. Let's move on then, ladies and gentlemen. Okay. We left off yesterday talking about trends of the periodic table. And we are on slide number 29, ladies and gentlemen, and oxidizing agents. Oxidizing agent is a substance that causes another to be oxidized. Okay? It is what is actually being reduced. Okay? Now, real quick, ladies and gentlemen, what does it mean to be reduced? What does it mean to be oxidized? Well, let's take a look at a very simple chemical reaction, ladies and gentlemen. That chemical reaction that we are going to look at is this. So we will say if we have silver metal plus sodium chloride aqueous will produce AgCl solid and sodium metal. Now everything here is balanced. What kind of reaction is this, ladies and gentlemen? Single replacement. Good. What is the charge of silver when it is alone, not with something? Nope. What is the charge of silver when it is alone and not with something? No charge. 0. What is the charge of sodium when it is alone and not with something? 0. Any lone element has a charge of 0. No charge because it has not gained electrons. It has not lost electrons because it is alone. What is the charge of sodium in a compound, ladies and gentlemen? +1. What is the charge of chlorine in a compound, ladies and gentlemen? -1. What is the charge of silver in a compound, ladies and gentlemen?
+2. +1.
+1. What is the charge of chlorine in a compound, ladies and gentlemen? Okay. Oops. All right. So now, ladies and gentlemen, now we are going to look at what we wrote down. So let's begin, ladies and gentlemen, with silver. Silver starts out as a 0. Over on the other side of this reaction, it changes to a +1. Okay? Its charge changes from one side of the reaction to another. Questions? Okay, let's take a look now at sodium. Sodium is a +1. Over on the other side of the reaction, it is a 0. Its charge changes, correct? Good. Excellent. Wonderful. Glad you're agreeing with me today. Then we will look at, ladies and gentlemen, chlorine. Charge of -1 on the other side of the reaction, still a charge of -1, which means what? That it does not change. Okay? Now, oil rig. Oxidation is losing electrons. Reduction is gaining electrons. For silver to go from a 0 to a +1, it has to do what? To go from a 0 to a +1 charge, what does it have to do? Well, those are the two choices. Which one? Which one? To go from 0 to a +1, what do you got to do?
You add 1, you gain 1, you share 1, you give 1.
Okay, if you're going to use the Dick Cheney method, we're not going to get anywhere. How do you go from a 0 to a +1? What do you do with electrons? You named me all three, but I only want one answer. I'm not going to pick it for you. You lose electrons. That's how you become more positive. So if you lose electrons like silver is doing here, ladies and gentlemen, that is the process of oxidation. Now, if you're going to lose electrons, something else has to gain it. What gained an electron here? No. -1, -1, it didn't change.
Na, sodium.
Okay, sodium went from a +1 down to a 0. That means it has done what? It has gained an electron, which means that is reduction, ladies and gentlemen. Questions? Am I going to make you do this on your test? Heck no. But now you understand what oxidation and reduction are in the basic form. Oxidation is when you lose electrons. Reduction is when you gain. Cynthia, I'm sorry, I keep cutting you off. Go ahead.
So you're not going to ask us anything about that, so we shouldn't write it down? Like it's nothing.
No, I'm not going to ask you anything about that, but oxidizing agents are substances that cause something else to be oxidized or what is reduced. The best oxidizing agent is fluorine. The best oxidizing agent is fluorine, ladies and gentlemen. So again, you've got your periodic table. Okay, you've got your periodic table here. Fluorine is up here in the corner, ladies and gentlemen. Fluorine is the best oxidizing agent. Which means, what is the best reducing agent? Francium. And again, as you get closer to those, ladies and gentlemen, you would become better and better at whichever one you're talking about doing. Being an oxidizing agent or being a reducing agent. Questions?
Wait. So if it's best at reducing, that means it's gaining electrons. For when it's not.
If it is an oxidizing agent, it is what is being reduced. They're opposite. The oxidizing agent is what is being reduced. Reduce is meaning you're gaining electrons. Fluorine is the best at that. Why? Because it's a nonmetal and it wants to gain electrons, right? So the best oxidizing agent, the best reducing agent would be the substance that causes another to be reduced, and it does that by being oxidized. And that would be the one that loses an electron the easiest, which is francium. Therefore, the worst oxidizing agent is fluorine. So if you're best at one, you're worst at the other. Make sense? I like the way you say that. I almost have confidence that you understand that. Okay?
So is this in like when you set up like a
So,
this,
okay.
this?
So let's say these two elements are next to each other on the periodic table, even though they differ by 11 in atomic number. Where's that got to be? These two elements are next to each other, even though they differ in atomic number by 11.
Oh, there's 4, 5, 6, or 7.
Fourth and fifth period, group 2 to group 13, correct? Group 2 to group 13, okay? these elements are in the same period as the number of electrons in half-filled d orbitals. How many electrons half fill the d orbitals? 5. So now we're in the 5th period, correct?
Yes.
The one named after the high point of a wave is a better reducing agent than the one named after the low point of a wave. What's the high point of a wave? What's the low point of a wave? And we know that they have to be in this spot right here or right here. So the one that is named after the high point of a wave is a better oxidizing agent. Where are the better oxidizing agents?
Right there.
Where?
49.
What?
The left side.
49. The right side.
Okay, thank you. No. Where is the best oxidizing agent?
The left side.
You said fluorine was the best
Yeah,
oxidizing.
Okay, sorry. I'm confusing myself. Yes. So yes, fluorine is the best oxidizing agent. 49 is closer to fluorine than 38. So the high point of a wave goes at 49, which is? Crest. What goes in 38? Trough. Questions? No, none, zero, zip, zilch? These are easier when you're looking at them. I'm making them up in my head as I go. All right, ladies and gentlemen, let's talk about radioactivity. Radioactivity is a spontaneous breakdown of the nucleus of an atom and it releases energy. This is not like a chemical reaction. A chemical reaction is the rearrangement of electrons around the nucleus of an atom. A chemical reaction is this metal loses an electron to this nonmetal. A nuclear reaction, one single nucleus of an atom, breaks apart, ladies and gentlemen, and becomes a different substance. Literally a different element on the periodic table. Why? Because depending on the type of decay it goes through, alpha, beta, or gamma, it will become a new element on the periodic table. Now, again, I would write this somewhere on your periodic table. I would probably write it on the bottom or on the top of this periodic table. Okay? Now, there are 2 types of decay, ladies and gentlemen. 2 types of decay, actually 3, but only 2 that actually change the nucleus of the atom. There is alpha decay. In alpha decay, for every alpha particle that is released, the atomic number decreases by 2. The atomic number, sorry, I need to put a little bit more into that, ladies and gentlemen. What I mean is, I did not put atomic number. Goes down by 2. So, if we start out with an element on the periodic table, ladies and gentlemen, like polonium, and it gives off an alpha particle, it will lose 2 protons. So its atomic number will go down by 2. What is polonium's atomic number? So if it goes down by 2, what does it become? It becomes lead. Or it becomes a spot of lead. Okay? So that is what happens during an alpha decay. Now, what if, let's say, element 117 lost 2 alpha particles?
MC.
What?
MC.
Nope. What? NH. You go down 2 for every alpha particle. If you lose 2 alpha particles, you would go down 4.
Wait, so how do we know how many alpha particles?
It will tell you in the question.
Oh, okay. So
So this element,
has
the element Name for the scientist who did the oil drop experiment. Is created when branium undergoes alpha decay and gives off two alpha particles. So you would find where branium is, wherever that would be, and you would go back how many spots? 4. 2 alpha particles. 1, 2, 3, 4. Okay? But guess what happens? If you got branium wrong, guess what? You just got milliken wrong too. Which is why, ladies and gentlemen, for the low, low price of 2 points, you can come up to me and tell me to place any element on the periodic table you want. And I will put it on there for you in the correct place.
Why?
Why? Because if it helps you get 2 or 3 other clues, that might be 2 points well spent.
So it says atomic number decreases by 2
Yep.
per alpha particle.
Yep.
Alpha particle broken
Like it'll
down,
literally say,
or-
during this decay it gives off 2 alpha particles.
Oh, so given off.
Yes, given off. That means they go away.
Yeah. Okay.
They take 2 protons with them. That's what happens during alpha decay. Okay? Now something different happens during beta decay. Okay? I'm going to go up to the top. Well, I'm going to go on the bottom. I know you don't. Hopefully you have room. I'm going to write off of my periodic table here. But anyway, beta decay is when a beta particle is released and this causes the atomic number to increase by 1. Because what happens during beta decay is a neutron in the nucleus of the atom breaks apart into a proton and an electron, thus creating a proton that was not there before. For every beta particle, it leaves behind 1 more proton. So instead of going back 2 places in alpha decay, beta decay, you move forward 1. So if lead were to undergo beta decay, it would become bismuth. Question. If bismuth were to undergo alpha decay and give off 1 alpha particle, it would become thallium.
Are these elements always going through?
Well, remember we said 82 on up are all radioactive.
They're radioactive. Are they always going through this process, or do they need something to trigger it?
It's spontaneous. It happens on its own.
It only
It's
happens
a
with
weird-
radioactive.
Only happens with radioactive substances. So, and some substances that happens very quickly. Francium, it takes 22.5 minutes for that to happen. Carbon, which has a radioactive isotope, takes 5,700 and some years. It all depends on what it is. Questions? And by the way, there is a third type of decay, ladies and gentlemen, which is gamma decay, but nothing happens to the nucleus, so we don't have to worry about it. It doesn't increase the protons. It doesn't decrease the protons. It doesn't change anything. Questions?
So are we still going, if it gains one, are we still going back 1?
No, you're going forward 1. That's what I mean.
Right.
So this one here would take your spot and move it back 2 for every alpha particle. This one will move you forward 1.
So let's say we're at the corner and it says it's 2. So
Which corner? Here?
Yeah, let's say we're there. No, up. Yeah, that one. If we keep on going this way, would we go?
You would go to the next one down here, yes. Yes. Good point. Thank you. Yes. Yep. Yep. The next one in line. Okay. Questions?
But that only means sort of radioactive, from lead and on, right?
Correct. Correct. Questions? Okay. Again, alpha or gamma decay, the atomic number doesn't change. We don't have to worry about it. Okay? Do you remember how I told you Mendeleev, when he created the periodic table, he had gaps? He had blanks in it. Well, when there were gaps, when there were blanks, he used the term, a prefix eka, E-K-A. And eka meant one below. Okay? So, for example, in his periodic table, tactinium didn't exist. It hadn't been found yet. But there was manganese. So that spot that was open, he called it eka manganese, meaning one below the one above it. So that until it got a name, this spot was called eka manganese. Eka means one below. Okay? So for example, I could give you a clue. If this is branium right here, this spot, and the clue is fercium was once called ecabranium. Where does fercium go?
Below.
One below where branium is. Again, possibly worth it to buy where branium is on the periodic table to get fercium correct if you're not sure.
But then we get branium wrong, and then the other ones will be wrong too.
But if
That's
you
why
buy
he
it,
says-
I will put it in the right spot for you.
We can only get one.
You can buy as many as you want. You can buy all 50 if you want to take a 0. I don't care. I wouldn't buy too many. But there are some times where 2 or 3 clues, depend on where you put one, might be worth it to make sure that one is correct. It's just an option I'm giving you.
Is it 100?
Wait, it's 2 points for
Yeah.
one?
Correct. There are 50 blanks, 2 points each, make a 100-point test.
Is this like what our test is gonna look like?
Yeah, except without the writing that you just put on
Should
there.
we,
Yeah.
should we write the prefix for everyone?
I would know that because the clue that I just gave you, the example that I just said, is probably going to be the test question.
What those examples?
I don't know. I could use any 2 elements. All right. So maybe bluogen was once called eka yellowium, and yellowium is right here. What does that mean for blue? Goes right underneath it. Goes right underneath it. Again, I would write that somewhere on that periodic table that we have, that you have.
Okay, right, what?
Eka means one below. Eka means one below. That is what eka means. Questions? We're good? Moving on along. Yesterday we talked about ionization energy. What was it?
Energy needed to remove an electron.
Good. But guess what? You can remove more than one electron. Matter of fact, for magnesium, you remove how many?
2.
2. For aluminum, you remove how many?
3.
3. For lead, you remove how many? Guess what? You could remove 5. You could remove 6. You could remove 7. If you gave it enough energy, technically you could remove 8. But sometimes it's harder to remove certain electrons. Well, ladies and gentlemen, ionization energy is the energy needed to remove an electron from an atom in its ground state gas phase. Yeah, we talked about that, right? What family has the easiest time removing an electron? No, the easiest time.
Alkaline,
Why?
because they only have one.
And they want to do what with it?
Get rid of it.
Good. What family has the hardest time removing the first electron?
Fluorine.
The green ones.
The noble.
The noble gases. Why?
They're not stable at all.
They are stable. Now, again, ladies and gentlemen, this is 100% up to you. How you want to do this, ladies and gentlemen. But if it were me, I would, first of all, take a picture of this. Snapshot. Boom. Good, 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 good. And now, ladies and gentlemen, I would take out this periodic table. Okay? Now, this is a family trend, correct? Okay. So here we go, ladies and gentlemen. In the first family, didn't touch anything, promise.
You do. Oh my.
Promise, didn't touch anything. Okay, first family. Shut up, you stupid thing.
That's not very nice.
I know. It shouldn't behave this way. Lowest, first, IE. What is IE? Good. If you can't remember that, I would write it down somewhere. I don't care if you abbreviate things, but you better know what your abbreviation means. Where do I put the highest first ionization energy? On the 18. Okay, good. And we said as you go across the period, ionization energy goes up. As you go down the family, ionization energy does what? Decreases. It's easier to remove the electron in francium than it is in sodium. Why? Because it's further away from the nucleus. It's less attracted to it. It's easier to get it to go away. Okay? Now, let's talk about first ionization energy. That's the energy needed to remove the first electron. Really, that's what we were talking about with ionization energy, right? The highest is helium in group 18. The lowest is francium in group 1. All I've done is added the fact that at the bottom of the family, it will be lower. At the top of the family, it will be higher. Are we okay with that? Still a family trend though, right? Okay, good. The second ionization energy is the energy needed to remove a second electron. What family has the highest second ionization energy? What family do you have the hardest time removing a second electron from?
Group 1.
Why?
Because they only have one.
Okay.
Because
Wait,
they
how
have
does
the
that
one that
charge?
they want
Never
to
mind, I don't
lose. But then once they lose the first one, they don't want to lose the second one because then they become stable.
Perfect. That is an awesome explanation. You were right, Ava, about they only have one. So when they lose that one, what do?
They're happy.
They become stable. They're happy. So now you're trying to convince it to give up a second one. Guess what? Because actually when they lose one, they're just like the what? The noble gases.
Isn't that what they want to be though?
Yes, which means now you ain't getting that electron from me. Ain't happening. Now, what family has the easiest time losing a second electron?
The alkali earth metals.
The which?
Earth metals.
What was the name again?
Alkali. Earth.
No, that's group 1.
Oh,
Alkali.
earth metals.
Alkaline
Alkaline.
is
Yeah.
group
Oh my
2.
god.
No, it's not. It is not. Now, you can think it's the same thing. You can yell at me. I didn't name them.
Yeah, you covered alkaline.
Where was
Sorry.
Covered the
Hey, bottom.
Yeah,
Say
they're
what?
all of them named.
What?
That's where I live.
Yes.
Thanks,
There you
Queen.
go. See? We would have got it wrong.
Alkaline.
Okay, so then you have to change your thing over there because that says alkaline metal.
Where?
On your
This is
wall.
Archidot.
Oh.
It's
Where on my wall does it say alkaline?
It says alkaline metal.
I've heard it referred to as alkaline. Oh, and alkaline metal is still an alkaline earth metal. Okay? All right. So, instead of yelling at me, let's go here, ladies and gentlemen. Okay. So, this group 1 has the highest what? Second ionization energy. Where is the lowest?
17.
No, come on. No.
17.
No.
That's what we just said.
No, it wasn't. Thank you. You guys are yelling at me about the alkaline earth metals, and you're over there talking about the halogens. So the group 2 has the lowest second ionization energy. Questions? That means no. Okay. What about the third ionization energy? You can tell me highest or lowest. I don't care. Tell me.
The highest would still be the first one.
Nope.
Highest is group 2,
Why?
because that's what you put down.
But why? I again, if you're just reading what I wrote, that's great. But why?
Because it loses 2, but it doesn't want to lose the third one.
Why doesn't it want to lose the third one?
That
Because
is
it's
high.
stable when it loses 2. So again, to get it to give up a third one now, doesn't want to. Okay, so let's go to here. Highest third ionization energy. Where's the lowest?
The
13.
Why?
It has 3 that it wants to lose.
Yeah, so hey, I got lost 2 already. Here, take the third, please. What's happening to our trend, ladies and gentlemen?
It keeps moving over.
Okay, so where is the highest fourth ionization energy?
13.
Yeah, 13.
Why?
Because it already lost 3 and it just wants to lose 4.
Loses 3, becomes stable, doesn't want to give up the fourth, does it? Where's the lowest fourth ionization energy?
14.
There's only 4 levels.
Yeah.
No, we could keep going. Do we need to?
No.
Where would be the fifth?
Highest 14, lowest 15.
Do you want to keep going? We can.
No, not really.
If
Okay.
it's not on our
Wait,
test,
is this
I
how
don't
you do
care.
Is this how
Oh,
you
it
do
is on your test.
How
Like,
high is it gonna go on the test though?
Well, I don't know.
more
It
than
all
4?
depends. Could go to 6.
Okay,
Well, where would be the highest sixth?
thanks.
15?
Okay, where would be the lowest sixth? Okay, do you see a pattern?
Yeah.
Okay, if you need to continue, please continue. If you're good, please, that's okay. All right, since you're yelling about this,
No one's yelling.
you were.
So ionization energy is the electrons they lose.
It's the energy it takes to lose an electron. How much energy it takes? It takes some, no matter what. Even francium takes some.
Right, because they want to become stable.
Right. Alkali metals, earth metals. Alkaline earth metals. Boron family.
Are you gonna take that? Are you gonna take it down? Or no?
I'm not. I'm not taking anything down in my room. But I also don't want to hear whining if you get stuck in a seat way in the back there and you're like, well, I don't know what the families are now.
So just walk us together.
So I'm just helping you out.
You guys want to assign seats?
Have I ever assigned you seats?
No, so
But if you're the last one in the room that day and there's a seat open in the back, where are you going to sit? That's all I'm saying. That's all I'm saying. Carbon family. Nitrogen family.
Wait, so one's alkali and one's
Alkaline.
Wait, so it's
Yes.
to remove an electron from an atom to stay stable, to become stable.
Just to remove an electron. It's literally just the energy to remove an electron. But the point is, once an atom becomes stable, it doesn't want to give up any more electrons. And at some point, when you take electrons away from atoms, they will eventually become stable. Even if you get to the halogen family all the way over here in group 17, if you take away 7 electrons from a halogen, it is stable because that's all it had in its valence shell. Now, normally, a halogen would rather gain 1 electron, but we're talking about forcing them to lose electrons.
Oh, okay,
So you can make a halogen lose 7 electrons. Then it becomes stable. Then it's like, oh, I'm happy. Okay. I didn't want to lose those other ones, but okay, since I lost them, I guess I'm happy now. So that's all ionization energy is. Group 16, ladies and gentlemen, is the oxygen family. Group 17, halogens.
Who named these?
They were named by, when they were found, they were put in a group, in a family together. When Mendeleev was setting up his periodic tables, he put things that were similar to each other, and he called them a family. Like, for example, siblings to you may have some similar traits to you. So he called them families.
But no, like the halogen and the alkali.
Halogens were called because those are what are called salt formers. That is probably the worst word salt I've ever written.
Looks like SRT.
Let's try that again. Halogen means salt former.
Do we need that?
Might. And finally, ladies and gentlemen, these are the noble gases.
What does it say on the family? What is it, 16?
16, oxygen.
Yeah, totally.
Noble gases are inert. What does that mean?
They don't change.
Kind of. They are what?
Stable.
Stable, which means they are unreactive, which also means they are monatomic. What does monatomic mean?
Not atomic.
No.
One.
One what?
One atom.
One atom. Why? Because they don't react with anything. They stay as one atom. They do not double up. They do not become a pair. All different ways of saying the same thing for the noble gases. Did you get the salt former? I'm sorry, it isn't written as great as it should be. By the way, what do the halogens like to react with?
The alkali.
The alkali metals. These right here are very reactive with water. Very reactive with water. These right here are slightly reactive with water. But these puppies, fun stuff happens.
Didn't you do that? I think freshman year you put
Yep.
potassium in with water.
Yep.
Did it
Yep.
again. It was fun.
Yep. Questions?
And then, which ones are very reactive? The rest of them?
Alkali earth metals.
Very reactive.
Very reactive.
And then slightly reactive.
Slightly reactive.
No, which
So
one
what
is
was
slightly?
Oh, it's not.
The alkaline earth metals.
Oh, so it's just those two?
Yep. Questions?
What's the 17? What does that say?
17, halogen. 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 Which means salt former.
So when
I'm listening.
they react with other, they form different
I'm
types of salts.
what?
So when-
Normally, a halogen will react with an alkali metal to make a salt, sodium and chlorine, table salt. But they could also still react with the alkaline earth metals.
and they still become some type of salt.
Yes, yes, yes.
Are we gonna have the transition metals on our test?
No.
Really?
Well, this is it. These are the groups.
Wow.
1 and 2, 13 through 18.
That's actually awesome, Mr. Bennett. Thank you.
You're welcome. Don't thank me yet, though. You haven't seen the test.
Any
Oh,
element
God.
that like mixes with salt, is that gonna be the halogens?
What?
Any element that like mixes with salt.
Well,
Or that
if the halogens are involved in a compound, normally we classify that compound as a salt. It's kind of like if oxygen is involved in a compound, we call it an oxide.
Which is like sand, salt. What else?
Sand.
I don't know.
Is that some type of salt?
No, sand is an oxide. Sand is silicon dioxide.
So what are types of salts?
Potassium chloride, sodium chloride, magnesium chloride, magnesium fluoride.
Wait, isn't that ions?
Well, remember, ions make up compounds. And if a halogen is in the compound, we generally call it a salt. Good. Questions? Yep. Yep. All right. There is a thing called Lewis structures, ladies and gentlemen, and we're going to get into this when we get into VSEPR in just a minute. Every alkali metal has one valence electron. You can write that down on your sheet if you want. I don't care. Hopefully you already know that. Because it has one valence electron, what charge will it have? Plus one. Alkaline earth metals have two valence electrons, which normally makes them a +2 charge. The boron family has three valence electrons, which except for boron makes the metals in that family have a carbon family has four valence electrons, or -4. Which ones are the -4s? Nope.
Non-metals.
The nonmetals at the top, the metals at the bottom would be the +4. Nitrogen has 5 valence electrons. No, -3. Why? Because it becomes easier to gain 3 electrons to fill this than to lose the 5.
What about the ones underneath it? Like the
Exceptions, we're not going to worry about them.
Oh, okay.
Oxygen family group 16 has 6 valence electrons. Nope.
Game 2.
Gain 2, fill in these 2 spots, right? Halogens have 7 valence electrons. Gain 1, fill it up, look just like neon over here with 8, correct? Okay? Questions? Now, tell me where this electron is.
First one.
What?
The first thing.
Well, it could be the first, but for lithium, it's in the second level. What is this one electron configuration-wise?
What do you mean?
2, what?
Two valence?
SPDF.
Oh, S.
2, 0, 0.
2, S, how many?
1.
1. What would sodium be?
2s2.
No,
2s1, 2s2.
no.
3s1,
2s1,
Oh, I was thinking
3s1.
4s1, 5s1, 6s1, 7s1.
Good. So that one electron right there is the S1, correct? So what are these?
the S2.
Okay, and that's beryllium. 2s2, magnesium 3s2, calcium 4s2, 5s2, 6s2, 7s2. All of these have 2 electrons, the S, the 2 of them, correct? So now we slide over to the boron family.
The P.
Okay, how many P's?
The 1 through 6 P's.
P1.
P1.
Oh.
You're right, there are 6, but there's only 1 needed here, correct? So what are these on top?
The S's. The P's.
And that's P1, correct? Okay, carbon. What? P2. 2s2, 2p2, correct? Explain it.
2s1,
Because it wants to
2s.
separate. Or it wants to be like.
Good. Term.
Isoelectric.
Symmetric.
For what?
Then-
Term for what?
For this, what's going on here? Because there should be 2 up here, 1 here, and 1 here.
Is it balance?
Because the 2 S's should be up here, 2p1, 2p2, correct?
Yes.
Somebody tell me what's going on here. Somebody give me the term. The term that I said you didn't have to know when it happens. but you should recognize when it did. And I told you carbon would do this.
Oh, oh, right.
Nope.
It's like when the transition metals have have the different charges
Oh,
based
like
on.
it jumps.
Good. What was the term?
Sick.
It.
Term for what?
The term for what's happening here.
So what's happening? I didn't understand.
The electron that's supposed to be up here in the S has moved into the empty P. Come on.
A degenerate orbital.
This is your degenerate orbital here, ladies and gentlemen. This is the degenerate orbital I was telling you was going to come back. Nitrogen, 5 electrons in its outer shell. 2s2, 2p, 3. It can't have a degenerate orbital. Why?
Because it's already filled.
Because these are already each half filled. Here, there was an empty one originally. So it took one of those, moved it over into here. Okay? Oxygen, 2s2, 2p4.
Wait, didn't you say that the P's go out? Oh, wait, that,
Singly first,
Okay, yeah.
then doubly.
Because I was.
But
thinking-
here, remember, S's should fill before P's. But one of these S's moves into here in a degenerate orbital.
So that way they can fill it up.
What?
So they can
Well, we'll see what that does in just a minute. Fluorine, 2s2, 2p5. Singly first, doubly. Not enough to fill that, right? 2s2, 2p6. All of them are filled, correct? Now, if we move down from neon to argon, all we do is change what? The energy level. Instead of 2s2, 2p6,
So
argon would be 3s2, 3p6,
okay, so
correct?
that means we move on to. So that's one.
So it's going to have the
We move on to-
same electrons in the outer shell, okay? It's just they're going to be in the third level instead of the second. Yes, sure, go ahead.
The third level is outwards, right?
The third level is lower. It's the next level down. Then you would go to the fourth for krypton. Then you would go to the fifth for
It
xenon.
just keeps going more.
But xenon will look exactly like this if we're only looking at the outermost electrons. That's what these are, only the outermost. Okay.
As it goes in, it's.
If it goes in, it doesn't matter. That we don't care about those here. We don't care about the D's and the F's here. These are only the S's and the P's. Questions? But oxygen looks like this. So would sulfur, so would selenium, so would tellurium. Technically, so would polonium and livermorium too as well. Okay? But these are metals. We're not going to get into exceptions. Fair enough? Okay. Well, there are 3 ways that you can fill your outer shell. You can gain,
Or lose.
you can lose,
Or share.
or you can share. Share is the one we haven't talked about much, ladies and gentlemen. So let's talk about sharing because after all, ladies and gentlemen, sharing is caring.
Oh, is it really?
So let's talk about VSEPR. Valence shell electron pair repulsion theory. VSEPR. Okay? That's what it means. And on the test, I'm going to ask you, what does VSEPR stand for? That wasn't the answer I was looking for.
Wait, what?
Sharing
Am on the test, am I going to ask you what does VSEPR stand for? No,
Oh, thanks.
because it's not going to fit into putting it on a spot on the periodic table. Okay. It's the model that explains molecular geometries based on minimizing the repulsion of shared and unshared pairs of electrons. In other words, the electrons want to do what to each other?
Cancel. Add. Share. Sorry. Share.
Attract.
Electrons, really? So 2 negative charges will now attract each other.
Cancel each
Stable.
other out.
They want to repel each other. They want to get as far away. VSEPR explains how they can get as far away from each other as possible when they combine with other atoms. But they have to be doing what with electrons according to VSEPR? They have to be sharing. They have to be sharing electrons. Okay? which means they're what kind of compound? Starts with a C, ends with covalent. Covalent, thank you. Good, awesome, nice job. Now, what kind of elements make covalent compounds? Ionic is in the word. Ion is in the word ionic. Why would you say ionic or covalent?
Wait.
What kind of elements make covalent compounds? What kind of elements make what kind of elements make ionic compounds? A what and a what?
Oh, a positively charged and a negative charge.
Which what are positively charged? What?
A metal and a non-metal.
Good. So what makes covalent compounds?
Two non-metals.
Two nonmetals. Good. Excellent. Wonderful. Some of that learning I taught you is coming back. When atoms form covalent compounds, they do so by sharing unpaired electrons. Now, if I am going to share something with someone, the only reason I am going to share something with someone is if they have something I want and I have something they want, correct? Okay? So Alexis has half of the winning lottery piece. I have the other half. Now alone, we got nothing. But together, we could share the jackpot, right? So we are going to take our pieces, we are going to share them, we are going to go down, we are going to claim our $1,000,000. Awesome. And we're going to split it 70-30. 70-30. Right?
No.
No? No? Well, that's too bad because your Itzy has the same piece you do. So, will you take 70% or 30% of $1 million, or will you take 100% of nothing? Okay, you're out. You can keep your piece. Point is, atoms can share evenly, or they can share unevenly. Remember electronegativity, the ability to attract and hold on to an extra electron? Some atoms want to hold on to electrons more than others. So guess what? If you give them an electron, they'll hold on to it more strongly than another one will.
So some atoms are scammers.
Yes. Very good. Awesome. Okay, a lot like guys. Anyway, each covalent bond is a pair of shared electrons between two atoms. So when you make a covalent bond, every bond is one electron shared by each atom. So you have an electron, I have an electron, we're going to share them to make a pair. Okay? Why? Because that gets us both closer to filling our outer shell. Right? Okay, good. Total pairs of electrons are the total pairs of electrons that are around what is called the central atom. Okay? The central atom. Bonding pairs is the number of shared pairs of electrons between the two atoms. Okay? So how many electrons pairs are shared between the two atoms? This will become a lot clearer in just a minute. Lone pairs are electrons around the central atom that are not involved with bonding with another atom. Okay, again, I can show you this. It'll be a lot simpler in a minute. Good? Good. The total bonding pairs and the total lone pairs determines geometry and the angle of the bond. The geometry and the angle of the bond. And the geometry and the angle of the bond is determined by how the heck can I keep these electrons as far away from each other as possible. Make sense? Good. Okay. The total pairs around the central atom determine something called hybridization. What is a hybrid? Mix of two things. A hybrid car is a mix of what? No, come on.
The electric car
And
the normal.
And the gas car.
Gas.
A hybrid car is a mixture of gas and electric. So your car will sometimes run on gasoline and sometimes it will run on electricity. That is a hybrid. Okay? Well, hybridization in an atom involves what electrons? The ones where? Okay. What kind of electrons are in the outer shell? What sublevels? The what? The P's and the S's. Now, a P and an S electron are very different. Okay, they have their own shape. But when they overlap, their shapes change. So when you and I share an electron between us, it's no longer a P1 and a P5 for me. It's now a hybrid of that. Okay? It's a hybrid. So there is what is called sp hybridization. Sure, go ahead. Okay? Hybridization is the overlap of atomic orbitals becoming molecular orbitals. So we're sharing our electrons, and when we share them, the shape kind of changes. Okay? So, when two atoms share electrons, they are no longer sps, ds, or fs. Now, we're not going to worry about d's and f's because they're not in the outermost shell. But understand, take AP chemistry, we'll talk about d's and f's. Because there is possibility for sharing those, ladies and gentlemen, because those aren't always filled. Okay? We're not going to, though. So we're just going to talk about S and P's. Okay? All of these compounds are between a representative of a family. What I mean by a representative of the family. Carbon family. Give me an element that represents the carbon family.
Carbon.
Or
Lead.
silica. Not lead, though. Why?
Because it's a metal.
Okay. We could technically say it, though.
But we're talking about covalent bonds, aren't we?
Correct. But here's the thing, and this is the honest to goodness truth. For every rule in chemistry, there's always n,
Exactly.
and there's no exceptions to that rules. Well, here's the other thing. Chemistry is very rarely black and white. Very rarely. So even though something is an ionic bond, guess what? There's a little bit of sharing that goes along with that. There is. And even though something is a covalent bond, well, sometimes it spends more time around one atom than the other, making it kind of ionic. So again, we're talking about trends. We're going to keep this simple. So a representative of the carbon family could be any of these. Any of these. We're going to say any of them. Even though these probably don't, still could be any of these, okay? What would be a representative of the nitrogen family?
Nitrogen.
And anything below it. Oxygen family, oxygen, and anything below it. Now, these are the main elements. Then we put something else with them, okay? We put something else to combine with them, something else for them to share with. So when we talk about the representative family, we are talking about the main elements. What do we put with them, ladies and gentlemen? Something that only needs one electron. Something that can only share one electron, ladies and gentlemen. What elements can only share one electron? Nope. Those are too good a metal. Those are not going to make a covalent bond. What elements only need to share one electron? Because it can only share one electron. Halogens. There's one other element besides the halogens that can also do this. Hydrogen. So hydrogen and the halogens can combine with carbon to become stable.
Can there be like multiple? Or
We're not going to. We're only going to say two different kinds of atoms. So with these representative families, we are either going to put a halogen with them or we are going to put a hydrogen with them. And here is why, ladies and gentlemen. Whether it is hydrogen, how many valence electrons does it have?
One.
One. Now, how many does it need to gain to become stable? What? One, because there's only room for two here, right? So it'll share this one. All right? Fluorine, how many valence electrons?
One. Seven.
7. So how many can it share?
Seven.
That one.
And then
Why? It's not going to share these. Why?
because they're paired up.
They're already paired up. So this could share one. If it shares one, guess what? Makes a pair here. Boom, stable. This could share one. Guess what? Pairs up, makes a stable, right? So these will act the same. Make sense?
So the S's and P's.
Well, this is an S. This is S and P's. But again, remember, hybridization. We're going to talk about that.
So if it was P's and D's, we wouldn't be able to combine them? With
Correct.
S's
We're
and
not
P's?
going to talk about combining P's and D's and F's. Okay?
Take a-
All right. So here you go, ladies and gentlemen. This is the whole thing right here. Now, technically, the alkaline earth metal shouldn't do this, but maybe it can kind of a little bit because beryllium is right near the nonmetals of boron, correct? Right next to it. So let's say beryllium decided to make a covalent bond. It's got 2 electrons, it can share them, right? Fluorine needs to gain 1. So one fluorine comes in and says, whoop, okay, I'm good.
What are they combined with? Oxygen?
It can't. We're talking about just with this family, halogens or hydrogen. So it takes a second fluorine to come in to share with the other electron, right? Because it has two. So how many total pairs of electrons would be around beryllium here? How many pairs? Two. So there are two total pairs here. Do you see why? Here and here. Okay? There are two bonding pairs. Why? Because they are in between two different elements. This is two bonding pairs. How many lone pairs are here? Zero. None. The geometry, ladies and gentlemen, would be this. A straight line. Linear. Why is this and this in a straight line? Because this is as far away as this can get from that. Valence shell electron pair repulsion. This geometry says this is as far away from this as I can get. Make sense?
So what is the parts in the middle are the
This is
P's.
the beryllium.
Yeah.
These are the fluorines.
So what's in between? The ones
These
sharing?
are the overlap of the S's and P's. Now, how many S's are there? One, right? How many P's are there? How many P orbitals are there? How many P orbitals are there? Try again. There are 6 P electrons. How many orbitals are there?
3.
3. So, how many P's am I using here? If this is an S, how many of the P's am I using? Show them to me. This is an S. Well, what's this?
P.
Okay, this is sp hybridization. We're using an S and one of the P's. There's only 2 areas involved here. This is sp hybridization. Straight line geometry.
What is SP squared?
Okay, what is sp squared? Well, if we go to boron, boron now has 3 valence electrons, correct? So it can share with 3 fluorines, right? So you have 3 total pairs, here, here, and here. 3 bonding pairs, here, here, and here. No lone pairs, because there's nothing on top here. Trigonoplanar geometry, 120 degrees. How many S's and P's are you using here? 3 out of the 4, correct? So one of them is an S. What are the other 2? sp2. That's the hybridization, because you're using 2 of the 3 P's. This is what it would look like. Now, trigonoplanar. What does planar mean?
Flat.
Flat. Why trigonoplanar?
Because it's
Because this is the way this can get as far away from this and this as possible.
but it can still be as far as possible. You do it
They
like
really
this.
don't like each other.
Like what? Like this?
Yeah.
I don't, this is still the same thing. All I've done is change its orientation. So that's the point.
So I'd be like,
You
the
just make it not
orientation is like
3D.
K and like
No,
X and Y.
orientation is how it's in space. This again, we're not talking about that orientation. We're talking about how this molecule is arranged in space. And you cannot talk about the S's and the P's and the D's in a molecule because those are for an individual atom. Okay? But we can say that we're using one of the S's and 2 of the 3 P's that are possible around an atom. So this is sp2 hybridization.
Mr. Brand, let me go early.
That's why we can't use the other ones that we're using for one.
I have no idea what you said.
Since we have 2, what is it, 2 elements?
Yes,
So we can't use
correct. We're no longer talking about S's and P's because now they're a hybrid of S and P's. This is sp2. Okay? I will be here. Where am I getting your corrections? I need them beforehand tomorrow, sure.
Do I erase my old stuff?
Nope, just put them on a separate sheet of paper. I've only been telling you that for 2 weeks now, yes. Tomorrow is the deadline. So Cynthia, the S's, P's, D's, and F's, they don't quite exist here because now we're sharing things between two atoms.
But since we're not talking about D's and F's, that's what we're at.
Correct. We're not worried about the D's and F's because we're only worried about the S's and the P's because those are the outermost ones.
Oh.
So this, because we're using 3 of those 4 areas, the S and the 3 P's, the PX, the PY, and the PZ, we call this SP2 hybridization.
So we're using the last one because we want to keep them as far away from each other, right?
And the geometry says this is as far away from each other as they can get. Okay? This is as far away as these 2 elements can get from each other. If there are 3, this is as far away as they can get.
Right. Because it's the S's and the P's are in the outermost level, and we want to get them as far away from each other, so that's why we're using
Correct, but they're no longer S's and P's.
They're
They're a
combined.
combination of them. Okay? Okay? Good. You're getting there, kiddo. What are you
I
laughing
still
at
have
me
a
for?
C in this class, and that doesn't look like it.
Well, you should have come in and you should have retaken some of your other tests and you should have come in and gotten some help beforehand. I can't help
I
that
was
you
at
didn't
a
do that.
B. I was at a B, so I was like, okay, what?
I know, and then it started dropping. And what did you do? Nothing.
It was at a B before this last test.
And you could get it back to a B if you
If I
come in
take
and
it.
did a retake and got a 75 on it. But it's going to be a B minus. And therefore I laid out your
I'll
options
take it.
for you.
But then, yeah, you said that I was still going to be at a C.
Well, I said if
I
you
don't
get
pass.
a 94 on the final, you will get up to a B. If you don't, then you will stay at a C.
But you said I'd get a C if I get 70 on this past test, if I retake it. I'll
Right,
be at a B minus.
right. But to keep that B minus, you would have to write a 94 on the final to keep it.
Okay.
Okay. So in other words, it's a pretty low B minus. And if you don't do really well on the final, it's going to drop you down.
Okay.
That's the point.
Okay.
So it's your choice what you want to do.
I'm going to retake it. I'll probably come tomorrow.
Well, you have to come in tomorrow because tomorrow is the last day.
Okay.
And I still need your corrections first.
Okay, I'm working on those.
Okay. I'm just letting you know so we're all clear.
Okay.
You want me to change your attendance?
Yes.
Okay.
Thank you.